All right. It's day 54, and we're dealing with permutations. And this has to do with the subset pattern that we've been exploring. So we have an input string called word, return all possible permutations of the string. So the order of permutations doesn't matter. This is like combinatorics issue. So these examples will make it clear. So we have bad. All the different ways you can arrange the letters B, A, D. That's what you see here. And we have same here, same thing. That's a lot of words. And this last example right here. Let me make it bigger for y'all. So all the different ways you can arrange bad, right? IDEK, whatever, and KOP. Now this is a LeetCode medium. Now, unfortunately, we need recursion to find the answer to this problem. N factorial is the number of permutations of a set of size n. So if you have, and if you remember what a factorial is, 3 factorial is 3 times 2 times 1, 4 factorial is, no, 6 factorial is 6 times 5 times 4 times 3, etc. to 1. That's what a factorial is, and that is the number of permutations. The number of different ways to arrange three things is 3 times 2 times 1, which is 6. There are 6 ways. And another obvious important step is if you choose an element for the first position, then the total permutations of the remaining elements are n minus 1 factorial. You have this diagram. We lock A. We have ABCD. We lock A. Then we have to arrange BCD 3 things, 6 different ways, and so on. And this is a simplification of what we're gonna do. We lock B, then we permute A and D like so, 2 different ways, A and D and D and A. Then we lock, we swap the same swap we did here, but we swap B and A this time. And then we permute B and D again, fix B, and so on. As you can see here, the solution involves swapping and fixing things and swapping them. So let's look at the swapping part, which is fairly simple. It's this highlighted piece of code here. You pass in a word, pass in the indices, and we first split it into an array. We split the string into an array, and then whatever we want to swap, the index we want to swap, we store it temporarily, put the thing in there, put the new one where the old one was, and the old one where I used to be. Then we'll join it back. That's what this is. Fairly standard pattern. It's like swapping characters. All right, now this is a LeetCode medium, so, and it has recursion. So what can I say but follow along? Okay. So this is our function that does all the heavy lifting. Permute word. We pass in a word. This is the result that's going to store everything that we end up returning. Okay, and we're first one. Another red flag is how we are passing this in here, and this is manipulating this internally. Right, this is not like a functional way to do things. Ordinarily you'd pass it in and then return, it would return, and then you'd is the return of this that we do, because again that means we're not making a clone, a duplicate of this result variable. We are editing it in place, editing the argument by reference, not by value. So we're not cloning this, for instance, and passing it back as a result here and then returning that. Instead, we're just manipulating things in here, and you'll see why. It's kind of simpler in this scope of things. So this is our recursive function that permutes a string, and we pass in a word, like we're passing in here, a current index, the first thing, and the result that we want to manipulate as we move on. So first things first, if the current index is the last word in the string, push that word, right, the current state of the word, and return. We're done with this particular part of the stack, which is a familiar term if you're familiar with recursion, or how recursion works. And And otherwise, if we're not, we get the current index wherever we are now. iterate on from that current index to the end, to the last word, the last character in the word. Then each time we do that, we swap the string for that current index and what is it, and every other thing, every other word in there. So the same way we fix B, then next we swap B and A, right? This and the word thing right after. Do some things down here. Then we swap B and D, right? B and D, right? So that's swapping that is happening here. That's what we're trying to show right here. We're looping through the entire length of the object and swapping and recursing. That's why it is recursing, going down and doing something similar, right? So that's what this looks like. So we're passing that swapped string, increment the index by 1, and passing the same result, because that result is this is a terminating condition for the recursion. It's a familiar terminology. That's when the result is being pushed, right? As you can see here. So yeah, very hard to follow. In practice, you want to stay away from recursion, but you can't avoid it at the end of the day. So that's what this looks like, right? We're fixing things, then swapping, fixing and swapping, fixing and swapping. Fix A, so nothing to swap in D, right? Then swap A and D like that, and then come back, then do it again, then come back, then do it again. Hard to visualize, I'm not gonna lie. Hard to visualize. Is there any point in going deeper in this video? I don't think so. You can, in your free time, you can see the code on GitHub, put a bunch of breakpoints. I've already set up, I got these practice input words you can use to inspect and see what exactly is going on in this piece of code and follow along. Medium, but in my opinion, should be hard. But let's look at the time complexity. And so time complexity is n factorial, bad times. I don't know, factorial and exponential, which is greater? So interesting question. Where n is the length of the input string, and the space complexity of the solution depends on the depth of the recursive call stack. The maximum depth is n, so the space complexity is O of n. We're not going to recurse any more than the total length of the characters, because this terminating condition, it terminates when we are at the last character of the word. So that's the depth of the recursive call stack for you. Cheers.